So it is my pleasure to welcome Sergey Fomin, who will talk about expressive curves.
Thank you. Many thanks for the invitation. It's my pleasure to be here. I've never been to Stony Brook, so this is the first time for me to visit, even if virtually. I'll talk about joint work with Shustin from Tel Aviv. And this work is a follow-up to an earlier paper that we wrote with Pasha Pulavsky, Zhenya Shustin, and Dylan Thurston at the end of 2017, and we substantially revised and expanded it this year. So let me try and explain the topic first. So I will start with a toy example. This is a theorem proved by Michel Rolle in 1690. If you have, well, everybody knows this theorem, I imagine, that a real polynomial has a critical point between each pair of real roots. So this theorem was extended by Cauchy to arbitrary differentiable functions. And that's what most people nowadays call Rolle's theorem. But originally, Rolle was actually an opponent of calculus. He thought it was not legitimate science. And he proved his theorem for polynomials only. And that, in fact, is the generality in which I will mostly need it. So here is a strengthening of Rolle's theorem, a stronger version. Suppose that our polynomial is known to have real and distinct roots. Okay, so it's a real polynomial still, but we are viewing it as a complex polynomial. And so by the fundamental theorem of algebra, it has, you know, well, everybody knows what's true. And suppose that all the roots are real and furthermore distinct. And then not only do we know that there is one critical point between each pair of consecutive real roots, but we actually know, like, this gives an exhaustive list. There are no other critical points, even over C. So in some sense, we can completely describe the locations of critical points. So notice that the original, well, not the original, but Cauchy's version of Rolle's theorem is an analytic statement. But in order to ascertain that there is exactly one critical point between each pair of consecutive real roots, we need algebra. We cannot just stay in the realm of differentiable functions. We need some kind of algebraic condition that will force this you know, strong version. So the question that I'm going to ask then is, what are the multivariate analogs of these results? In particular, bivariate, when you have polynomials of functions in two variables. So let's start with Rolle's theorem, in Cauchy-Rolle theorem. So we're looking at a curve given by equation like this. Let's assume it's a nodal curve, so there are no like complicated singularities. All the intersections are just transversal crossings. And well, what can we say? Well, one thing we can say right away is that in each bounded region like this one, we have somewhere here we have a critical point, right? Because we have a real function which is you know, vanishes on the boundary and it's continuous. So it must have a maximum or a minimum, maybe both. Maybe there are some saddle points in between, so forth. And of course, each crossing is a saddle, right? because our function is positive here, it's positive here, negative here, or maybe it's the other way around. And so, you know, our camel has humps here, here, and here, and our legs go to the left and to the right. So, you know, it's a saddle. All right. But how can we make sure that all critical points are accounted for? Like the analog of the strong Rolle's theorem would require that inside each of these bounded regions, like this region, for example, there is exactly one critical point, right? It doesn't look like that's true about this particular function, but maybe I'm wrong. So what condition do we need to impose on G, on this equation, so that that condition would imply that inside each of these regions, bounded regions, there is exactly one critical point, which is a maximum or a minimum. There is a saddle at each crossing, and there is nothing on the outside here or here or here, right? And there are no other critical points, even over the complex numbers, right? That would be the two-dimensional generalization of the strong Rolle's theorem. All right, so here comes the main definition, which I just motivated. So we call a curve expressive if it comes from the following construction. So first of all, G is now, let's set up notation. So G is a polynomial with real coefficients. C is an affine curve, which is the zero set of that polynomial. And C sub R is the set of real points of that curve. And we call this polynomial or the corresponding curve expressive if it satisfies these conditions that I just described. So again, back here. So I want each bounded region to have at least exactly one critical point inside, necessarily real. I want each of the nodes to be a hyperbolic node, to be a saddle point. And I don't want any other critical points anywhere in the affine plane, even in the complex affine plane. Okay, so that's what this definition is saying. All critical points are real. I also want them to be Morse. So I want at each critical point non-degenerate Hessian. And then I want each bounded component to contain exactly one critical point. Each unbounded component contain no critical points. And also I want this to look like a curve. So we have infinitely many points and be connected. Okay, the set of real points to be connected. So that's the definition. Why I call it expressive, because it's sort of the real portrait of my curve, you know, expresses everything about how my curve behaves. Somehow the yoga is that it's enough to just look at the real portrait and then you know all the essential information about the curve. So this is an example of an expressive curve. So the equation of this curve is a product of three polynomials, P, Q, R equals 0. These are the polynomials whose zero sets are these circles, okay? It turns out, it's not at all obvious, that for any collection of circles which pairwise intersect in 2 points, the corresponding curve is expressive. And you can see an illustration of this here. So these dotted lines are the isolines, you know, the level sets of my polynomial. Okay, the blue ones are, you know, below freezing and below 0, and the red ones are greater than 0 level sets. Okay, and you see there is a minimum here, there is a maximum here, and on the outside there are no critical points. And moreover, I assure you that there are no complex critical points either. This is an example of a non-expressive curve. Oh, I lost connection too. Do you see my, oh, now you see it. Okay, so this is now an equation of the form PQ equals 0, where P equals 0 is an equation of this circle and Q equals 0 is the equation of this ellipse. And you can see that this is not an expressive curve, right? This is a non-example because there is a saddle here and there are two maxima here and here, okay? This in spite of the fact that the topological portrait is the same as the one for two circles, right? So there is something different about two circles from the picture where you have one circle and one ellipse. And we will see very soon, well, at some point we will see what's different. So our main result, which I'm going to present in maybe 30 minutes from now, is a complete classification of expressive curves, subject to a mild technical condition. And of course, well, not of course, but one of the key questions that I'd like to ask is, why should I care? Well, this may seem strange, like this is a super important problem, like in continuous optimization, you are trying to find a maximum or a minimum of your function and you use something like steepest descent method or something else. And you know, you want to be sure that the local minima and maxima that you found are indeed, you know, the complete list, right? Or if you are doing it in some bounded domain, that, you know, there is nothing, that you haven't missed anything, right? Using any of those iterative methods. So from point of view of optimization or analysis, if you want, this is a kind of, this is clearly an important problem. But the key word here is I. Why do I care? Me being a combinatorialist, right? This is not a question in combinatorics, like why, how come I got interested in this kind of things? And let me answer that question. Not why should you care, but why do I care? Maybe you don't care why I care, but I will impose this on you anyways. I keep losing connection with my, okay, I don't know what's happening. Okay, so the first motivation, which I will talk about only briefly because it's a work in progress, is extending the theory of hyperplane arrangements. So it turns out that many important invariants of an expressive curve, or more generally hypersurface, because this can be, you know, straightforwardly generalized to higher dimensions, they appear to be controlled just by the combinatorial topology of the set of real points. Like how these lines in this case, so this is a line arrangement here, right, on the left. And, you know, once we know how this looks like, how many nodes we have, how many regions we have, how many bounded regions or unbounded ones, what's the intersection lattice here, then you can recover from that information. It is kind of classical subject by now. You can recover information about the complexification, about the topology of the complement of the complexified arrangement, things like that. So somehow, it's well known that the real story tells you a lot about the complex story. And the idea is that this is actually true not just for hyperplane arrangements, which by the way, all are expressive. There is a simple log concavity argument that shows that any picture like this, where you have a bunch of lines, no three intersecting at a point, gives you an expressive curve. But in fact, what I expect is that the same is true, the same kind of theory is true for configurations of, let's say, parabolas or nodal cubics and things like that, which I will later explain are all expressive. So that's one direction of research, which I will not pursue here. This is all just right now a dream. I will tell you more about the second motivation, which is developing a global counterpart, what I call a global counterpart of the theory of morsifications of isolated plane curve singularities. So this is a very classical subject developed in the 70s by Arnault and his school, well, also Norbert Acampo. So what was that about? Well, you take a singularity, you are interested in its topology, in the local topology up to homeomorphism of what's happening around the singular point. So this is a specific example. Here we have two cusps in the plane which are kissing each other, and they're kissing, you know, they have the same, they're sharing a cuspidal tangent, right? And a morsification is a real nodal deformation which has the largest possible number of hyperbolic nodes, or equivalently, it has these features of expressivity that I just talked about, that you can see all the critical points directly here, locally. By locally, I mean in the vicinity of the point which used to be singular, right? So, you know, generically, when you deform a singularity, it gets as many critical points as the Milnor number at that point. And you want that Milnor number to match the number of critical points that you immediately see when you look at your picture. Namely, you see one critical point inside each of these regions, and you see a critical point at each crossing, you know? And 15 in this example. That's exactly the Milnor number of the singularity, and this is why this is a morsification. So one thing that we did with Pasha, Zhenya, and Dylan was to connect this theory with cluster combinatorics, with combinatorics of cluster algebras. And I just want to use an excuse of this talk to tell you about that connection, and also tell you that of a dream that we have, which is actually close to being realized, to extend these connections to a setting where instead of looking at a singular point at under a microscope and seeing this morsification as something which is happening near a singular point, we shook our curve a little bit, and our complicated singularity disintegrated into a bunch of simple nodes. We could play the same game, but instead of looking under a microscope, go far away and look at our plane from far away and intersect it with a disk and see a picture which looks very much like a morsification. But again, we want this condition of expressivity, which is the analog of the Morse condition in the local theory. Okay, so let me tell you more about this. So when we have a nodal curve in the real affine plane, we can define what Acampo calls a divide. So a divide is not maybe a good word, but it's already used in the literature. I would call it a doodle. So you just take, you know, you or maybe your granddaughter takes a pencil and draw something, you know, something like this, you know, and maybe, you know, you start with a disk, and then you take a pen or a pencil and you draw something, and then you draw something else, and then you draw maybe something closed. Okay, so this is how a divide looks like. So it's a union of immersed circles and intervals which intersect each other and themselves transversally. You know, I could give a formal definition, but it's clear what it is, right? And we are considering it up to isotopy. So that's what a divide is. Basically, it's like a curve, except we just don't care about metric or algebraic properties of it. We just look at it as a doodle in the real plane. And in the local version, of course, it will come from a morsification. In the global version, when you look at a curve, let's say real algebraic curve in R2, what I want you to do is to go very, very far away, take a huge circle centered at the origin and intersect it with your curve. Okay. So that's what's a divide. You have questions? No? Okay.
Can I ask a question?
Yes, sure.
Can you see a bit precisely what do you mean by looking from far away?
I just mean intersecting. I'm intersecting C sub r, the set of real points, with a ball, you know, with a set of points x squared plus y squared less than or equal than r for some very large r.
Okay, thanks.
Right? That's what I mean. But of course, r may be 1,000,000 and my screen is small, so I would have to, you know, compress it to show it to you, right? That's what I mean by looking from far away. Okay, so now one of the theorems which Ocampo proved actually much later than the original theory of morsifications was developed is that the divide itself determines the topological type of the underlying singularity, or equivalently, the link of the singularity. It's well known that the link of a singularity, which is the intersection of a small sphere surrounding the singular point with the complex curve, its isotopy type determines the topological type of the singularity. And so Ocampo proved that just by looking at the divide of a morsification, you can recover this link. And what we expect is that the same will be true for expressive curves, except instead of looking at the link of the singularity, you need to look at the link of infinity of your curve. You need to intersect your complex curve with a huge sphere of a very large radius, right? Of course, these links at infinity have been studied extensively by, you know, people like Walter Neumann and others, and that's what we expect to recover in this setting. So how exactly is this information recovered? Like, how can I get from a doodle to a link? Let me explain that. And I will do it in a somewhat unusual way using this cluster combinatorics. So first, let me tell you what these Playbig graphs are. So Playbig means planar bicolored. So they were introduced by Sasha Postnikov. And what they are really are, okay, let me show it an example, maybe draw something. So it's a graph, again, in a disk. And I want it to be, sorry, and I want it to be bicolored. So some vertices are black and some are white, but actually here they are red and you know, hollow. And I don't require that my graph is bipartite. So a black vertex can be connected to a black, you know, a black to a black, white to a white, whatever, right? But I want my graph to be trivalent in the interior. So each of these vertices has 3 edges coming out of it, and on the boundary, just 1 edge. Okay, so a picture like this is called a Playbig graph. All right. So now, again, we view them together with an embedding and up to an isotopy of the ambient disk. And now the point is that any divide, in the sense of that I just described before, gives rise to a Playbig graph. And the way it does is that we replace each crossing by a roundabout, right? So if you drive, you know what a roundabout is. Maybe you call it rotary. So instead of having a crossing of 2 lines, we build in this kind of piece. Okay, and this is an example. So this is a morsification of E6 singularity, and this is what comes out of this divide of this doodle when we apply this this technique, right? Each crossing got replaced by a roundabout. Of course, you may wonder, there are 2 different ways to choose colors here, and it doesn't matter which one you choose, because we are going to consider these graphs up to certain local transformations one of which is going to change colors in exactly this way. Take a roundabout and change all its colors. Okay, but there is also a canonical way to color them, but let's not worry about it. So there is an amazing construction due to Tomoe Kawamura, which we adapted to this setting, that associates a canonical link in S3 to any Plaby graph. And what you do is the following. You start with your graph, and then you replace each of its edges by two lanes. You know, like these are roads, right? So somebody is driving in this direction, somebody is driving in that direction, okay? And similarly here. So here in this country, we drive on the right. So I'm drawing like this. And now all I need to tell you is how to connect things near vertices, okay? And there are three types of vertices: black, white, and the ones in the boundary. So, and that's the recipe. So at a black vertex, I'm going to turn left. Everybody is turning left. At the white vertex, everybody is turning right. And when you approach the boundary, you just do a U-turn. Okay, so that's one part of the recipe. And now where is the link? And to get the link, you do the following. You consider a unit circle bundle over your disk. Okay, so over each point, there is the fiber is unit vectors sort of rooted at that point. And which unit vector we choose? Well, the tangent vector to our doubled curve, to our doubled graph, sorry, right? So above this point, let's say, you know, I pick the point in the circle bundle which corresponds to this unit vector, okay? So strictly speaking, this will give me a link in the solid torus, right, in the unit circle bundle over over the disk. But in fact, you know, this construction naturally gives a link in S3. I can explain that, but let's now not worry about it. So there is a construction of a link, very natural construction, and in the case of graphs coming from divides, we recover a recipe suggested by Acampo many years ago. More importantly, that link that you build turns out to be isotopic, in fact, transverse isotopic. So this link is actually transverse with respect to the standard context structure in S3. So you get a link isotopic to the link of the singularity, the classical Hegardt-Burau-Zariski link of a singularity. So that's the way in which you can recover the local topological information from the combinatorics of your divide, of the doodle. And we expect that exactly the same construction will recover the link at infinity in the case of expressive curves. Okay, questions about this slide? All right. Now, let me explain a little bit more about these Plaby graphs. So first, there are local moves on them. So these are like, there is a skein algebra associated with this business. So we can, first of all, do these flip moves. So we can take these 2 points and bring them together and then uncontract in this direction. Okay? You can easily see why I call it a flip move, because for the dual graph, this would mean that I am, you know, passing from one triangulation of a quadrilateral to the other. And then there is this, the interesting move is the square move, where I take a local picture that looks like a roundabout with alternating colors, and I change the colors as, you know, to the opposite ones. And so why is this a natural thing to consider? Because it turns out that these operations do not change the isotopy type of the associated link. Okay, so the link of a Plaby graph doesn't change when we apply these local transformations. So the natural thing to consider is really not a Plaby graph, but its equivalence class under these skein transformations. Questions? All right. More importantly for me, any Plaby graph defines a quiver. A quiver is just a fancy word for an oriented graph. How do we define this oriented graph? We place, so the quiver is here shown in red. We place a vertex inside each bounded region, and then we connect them across the edges of the graph, but only those edges whose endpoints have different colors. Like for example, here we have black and black, and so this edge doesn't have any red arrow going across it. But if a white vertex is connected to a black one, then there is an arrow going across, and it is oriented so that you would see black on your right as you drive along that arrow. Okay, that's the definition of the quiver. Okay, is the definition clear? Okay. Well, turns out that if you apply this recipe to the Plaby graphs coming from morsifications, then what we recover is the oriented version of what's called a Ocampo-Gusein-Zadeh diagram. So of course, every quiver defines a skew-symmetric matrix whose entry tells you how many arrows connect I and J, and which direction, you know, the sign of that entry will tell you whether the arrow goes from I to J or from J to I. And therefore, it will be skew-symmetric. So this will be the matrix of an intersection form for certain distinguished bases in the space of vanishing cycles. So so it is the classical construction, which I'm not going to recall here, but I'm just telling you that everything fits neatly together with the classical setup of the theory of morsifications. So now, what's important to me is that when we do local moves on arbitrary Plaby graphs, what happens to the quiver is something called a mutation. So there is a combinatorial notion of a mutation which can be associated to any quiver. Doesn't have to be planar, doesn't have to come from a Plaby graph. There is just a general definition which Zelevinsky and I introduced, which is foundational for the notion of a cluster algebra. And so it turns out that these local moves on Plaby graphs that translate precisely into mutations of the corresponding quivers. And so what we have here is that when we do move equivalence, when we do these scale moves on Plaby graphs, that on the one hand, they preserve the link associated to the Plaby graph, which, as we know, in these geometric settings has intrinsic topological meaning. At the same time, it preserves the mutation class of a quiver. Or if you wish, if you know what it means, it preserves the associated cluster algebra. So what this suggests is that there is, in fact, and we actually stated as a precise conjecture, that these relations are actually, you know, they go all the way. That there is a natural bijective correspondence between objects here, you know, which are of topological nature, and objects here, which are of cluster theoretic nature. So to make it precise, so we conjecture that quivers are mutation equivalent when they come from morsifications, if and only if the underlying singularities are topologically equivalent. And similarly, in the setting of expressive curves, the links at infinity should be the same. So why is this of any consequence, you may wonder. Like, if you don't care about cluster algebras or things like that, like, why is it even, you know, should be interesting? Well, let me just give you this baby example. So these are 4 morsifications of the same complex singularity, namely 4 lines transversally intersecting at a point, right? So we take 4 lines, they intersect at the same point, and then we morsify it, which means we, you know, locally deform it in a way that, you know, satisfies the morsification requirements, so that all the critical points are visible to a naked eye. This is one way in which you can do it. Just move these 4 lines a little bit, right? This is another way. How? Well, because, you know, it could have been that 2 of our lines were complex conjugate lines, right? And the equations were x squared plus y squared equals 0, right? So one line was x plus iy equals 0, and another line x minus iy equals 0. And when you morsify it, you get a little circle, right? And that circle is just as good a morsification as a pair of 2 crossing lines. And so we get this portrait, which is very different from just looking at the black stuff. Don't look at the red stuff yet. Just look at the black stuff. So we have these four pictures in black, which represent 4 different portraits, 4 different divides that you can get by morsifying the same complex singularity. But it's still the same complex singularity. How do we know? How can we reconstruct it? How can we, what is intrinsically the same about these 4 real curves? And a conjectural answer is that there is some cluster algebra associated to them, which is the same. How do you build that cluster algebra? Well, you build this quiver by the recipe that I just showed you. And lo and behold, these quivers turn out to be mutation equivalent to each other. So there is a sequence of mutations. I didn't define for you what mutations are. Of course, this would take another 15 minutes to get you familiarized with this. But there is some cottage industry, as you can imagine. You know, people are studying this, so they learned by now how to deal with these things. And so there is certain operation, there is software to deal with it, and there are, it's complicated to detect whether 2 quivers are mutation equivalent, but you know, people learn how to do it. And besides, this kind of combinatorics arises in many other contexts. And so if we understand what this cluster algebra is intrinsically, then this would really illuminate possible connections between plane curve singularities or these expressive curves and some other mathematical context. All right, so just very quickly. So what do we have? We have a curve, or maybe a germ of a singularity, right? And from that, we get a divide. From a divide, we build a Plaby graph. From that, we get a link, right? Which we consider up to isotopy. So this is the geometric story. We know we understand it pretty well. Now there is another more mysterious combinatorial story where we, from the Plaby graph, instead of going to a link, we go to a quiver and then build some cluster algebra. And that thing should somehow be intrinsically in correspondence with the topology of the original curve. And I have no idea what that correspondence is. There is a recent preprint by Roger Casals which suggests some potential connection in terms of symplectic topology, but I haven't digested it yet, and it's still conjectural. All right, so this was an explanation of my motivation. Now let's go back to the question, to the teaser that I gave you at the beginning, to the question of understanding who these expressive curves are. So this is a reminder of the definition, right? So we want all the critical points to be visible to the naked eye, right? So one extremum inside each bounded region in R2, and a saddle at each node, and nothing else, right? So to state our criterion, we will need some preparations. So I denote by L infinity the line at infinity, which is given by, in projective coordinates, by z equals 0. And I identify the affine complex plane with the complement of P2, that line within P2. Okay, so here comes my mild technical condition. It's called L infinity regularity. So what I want is I want the polar curves for my curve, you know, these curves which are given by, you know, vanishing of the partial derivatives. I want them to intersect at infinity. So here P is a point on the curve at infinity. I want them to have the multiplicity of their intersection, which matches the expected value once you know the Milnor number at that point. Okay, so again, I'm not requiring that my curve or the polar curves or anybody intersects things transversally. It could be very, very deep singularity there. But once I know what kind of singularity I have, and once I know what is the you know, the multiplicity of the intersection of my curve with the line at infinity at that point, then there is a certain predicted value for this intersection number, and I want that predicted value to match. Okay, so in order for that not to match, you have to really, really work at it. Like every expressive curve, for example, of degree at most 4 will automatically satisfy this condition. So you won't be able to come up with a real algebraic curve that doesn't have this property if you don't like work at it for a while. So this is really a very mild condition. Okay, just take my word for it. Now, I will also need the notion of a polynomial curve. So a polynomial curve is just a rational curve. Not just a rational, but it also should have a polynomial parametrization where both P and Q are polynomials. Okay. So, of course, I'm interested in real curves. So P and Q should be real polynomials. And it's well known that this is the same as requiring that our rational curve has one place at infinity. And then there is a companion notion of a trigonometric curve. A trigonometric curve is a curve which has a parametrization by trigonometric polynomials. So P and Q, again, are real polynomials, but now you plug in cosine and sine in it, right? And then, you know, like an ellipse will be a trigonometric, a prototypical example of a trigonometric curve, right? Okay, and of course, these are precisely the real rational curves which have 2 complex conjugate places at infinity. Okay, that's not hard to show. So now our main theorem. Suppose we have a plane algebraic curve with real irreducible components. And suppose we know that it is L infinity regular, this mild condition that I imposed. Then it is expressive if and only if each component is either trigonometric or polynomial, and all singular points in the affine plane are hyperbolic nodes. Well, and this is the third condition is pretty mild, that the set of real points is connected. Okay, so what is this saying? This is saying, first of all, in order to be expressive, every irreducible component has to be rational, right? Not just rational, it has to have at most two places at infinity, and it has two, they have to be, you know, complex conjugate. And moreover, these connected irreducible components should intersect each other only at real points. They cannot intersect each other at complex points, okay? And those intersections should be hyperbolic nodes, you know, not elliptic nodes, hyperbolic nodes. So this, let's go back to the example at the beginning. When you have two circles, right? Of course, these are two conics. They intersect at 4 points, right? But the other 2 points are at the line at infinity. That's okay. We're only looking at the affine plane here, okay? So all the intersections of these two affine curves in C2, they are hyperbolic nodes, these two, right? When you take a circle and an ellipse, they still intersect at two real, there are these two hyperbolic nodes, right? But the other 2 points are now not at infinity. They are two complex conjugate points, right? Not at infinity. And therefore, it's not expressive, okay? So in particular, still, it's not so bad. You can take any polynomial or trigonometric curve. Let's say somehow all its singular points away from infinity are real hyperbolic nodes, then you do have an expressive curve, right? So in spite of the fact that this is a rather restrictive property, the zoo of expressive curves turns out to be surprisingly rich. And I'm going to show you pictures and examples of expressive curves. But before I do that, let me ask you if you have any questions about the main theorem. And maybe you want, well, I didn't tell you how we prove it, but yeah, I don't have time for that, but I can wave if you want. Any questions? No questions. All right. So first of all, we develop many constructions that can be used to build new expressive curves from existing ones. Here is one example. We start with something which is obviously expressive, this parabola, okay? So it's really very easy to see that this is an expressive curve, this one. And of course, you know, a parabola is a polynomial curve, so it satisfies the criterion. Now what we do is we bend it. How we bend it? We bend it by a biregular real automorphism of the plane. Okay, obviously any such thing would preserve expressivity, right? Because critical points are mapped to critical points, and if we had them all under control, we still have them all under control. So I applied such a biregular transformation, and I got this kind of beak shape. It still looks like a parabola. I mean, topologically, it's still like a parabola, but algebra geometrically, it's a completely different curve. It's a, it's a certain quartic, a rational quartic. Now what I do is I apply this transformation. I replace y everywhere by y square. Okay, and under certain conditions, this can be done. There is a condition, and the condition being that well, okay, I don't have time to explain. But basically what happens now is that I draw this line, which is tangent here and intersects here and here, okay? And all the interesting stuff involving my curve happens above in the upper half plane. That's essentially the condition. And then I double my curve, right? So the portion above this line is exactly like topologically, it's the same as the thing on the left. And because I'm squaring stuff, so the lower portion is the same as the upper portion. And now, lo and behold, what I got is a limaçon de Pascal, which is a fairly complicated quartic curve. And I claim that this curve is expressive. I mean, we have a theorem to that effect, which I didn't state, but there is a theorem that says that this kind of operation preserves expressivity. And notice it's here, the geometry of this limaçon is very different from what we had before. It now doesn't seem even likely that the only extremum that you have, the only critical point that you have inside this region, you know, is a maximum or a minimum, that there is just one of them. It seems more likely that you have like two maximums and maybe a saddle here in between or something like that. But it's true. Okay, so here comes the first animal in my zoo. So this is a collection of lines. So I told you, any line arrangement is an expressive curve. Arrangement of parabolas. Of course, what we need, again, to ascertain each parabola is an expressive curve. All we need to make sure is that all the intersection points between these parabolas in the complex, I emphasize complex, affine plane are actually real, right? That's what we need to. And once we ensure that, then we have expressivity of the resulting curve. A circle arrangement I already discussed. We can take both circles and lines, okay? Now, let me just, this is a problem in calculus. Take the equation of each of these circles and each of these lines, multiply them out, you will get an equation, a single equation, which defines this curve in the plane, okay? Some polynomial equals 0. Prove that this polynomial has a unique critical point inside each of these connected components, right? I have no idea how to do it without using our general theorem, okay? This is a statement that can be explained, you know, to an engineer, somebody who may potentially be interested in finding, you know, actually finding minima of such functions. Well, a nodal cubic is an expressive curve, and again, placing them strategically with respect to each other, you can get more complicated arrangements, which are, again, expressive. This is a really interesting example. So these are so-called Lissajous curves or Lissajous-Chebyshev curves. So these curves are obtained, you know, they are parametrized by Chebyshev polynomials. This kind of parametrization. You take your two favorite Chebyshev polynomials, and T is your parameter, and then this is parametrization. So it's a polynomial curve, and luckily, not only it's polynomial, but it has enough real nodes, you know, to satisfy our restriction. Because if you just put down two arbitrary polynomials, right, that won't be satisfied because you have a rational curve. You know, a rational curve has lots and lots of nodes by Hironaka's formula. So, and you want all those nodes to be real. So you want your curve to intersect itself many, many, many times. And these Lissajous curves, they do exactly that. Another example of curves which do exactly that are Hypotrochoids and epitrochoids. So what are these guys? So you take a wheel, you run a wheel inside another wheel, right? So you have a big circle and then a small circle, and this small circle is rotating, you know, inside the big one, and there is a point here somewhere, not at the center, not on the boundary, somewhere here, where you stick your pencil in, okay? And that pencil traces a curve as the inner circle is rotated around the bigger one. If it is rotated on the inside, it's called hypotrochoid. If it's rotated on the outside, it's called an epitrochoid, okay? Either way, if the ratio of these two radii satisfies some conditions that maximizes the number of self-crossings of the resulting curve, then that curve will actually be expressive. And again, and here you see the Limaçon as one example, actually, of such a curve. So, and to finish, let me discuss pseudoline arrangements again. Not line arrangement, but pseudoline arrangement. So what is a pseudoline arrangement? It's a divide in our old terminology. It's a doodle where you have branches which are embedded intervals, and they intersect pairwise in the way that lines should intersect, meaning any two intersect at most once. So maybe once, like here, or maybe like here, they don't intersect at all. Okay? So, you know, it's a combinatorial concept. Some of you may be aware of the fact that not every pseudoline arrangement is stretchable. It can be represented, you know, can be deformed isotopically to a configuration of straight lines. This has to do with existence of non-realizable oriented matroids. So one can ask, when does such a thing come from a morsification of a plane curve singularity? And the answer is, any two pseudolines must intersect. That's the requirement. So, and of course, then you know which singularity you're resolving, namely just several local branches transversally intersecting each other. You can also ask, when does such an arrangement come from an expressive L-infinity regular curve? And the answer, surprisingly, is it comes if and only if it is stretchable, meaning, you know, if it can be represented by configuration of straight lines, not just pseudolines. Now, why did I bother you with this, with these two propositions? Because what it follows from them is that the divides that come from morsifications don't have to come from expressive curves, and the divides that come from expressive curves don't have to come from morsifications. That because these two conditions, that any two pseudolines intersect and that it is stretchable, they are in general position with respect to each other. There are configurations which are stretchable, but not any two pseudolines intersect, and vice versa, it can happen. And so what this shows is that maybe there is some master theory which sits on top of these two theories, you know, the local theory of morsifications and the global theory of expressive curves, which somehow encompasses both of these. And I am not sure what that could be, but it seems natural to me that such a theory must exist. And that's all I have to say today. Thank you.
Yeah. Thank you. Any questions?
I have two questions.
Okay.
One is non-mathematical. I was just wondering what application you are using for the presentation. I think it's quite nice.
I'm using GoodNotes.
Ah, okay. So, okay, great.
$7.99, I think.
All right, thank you. And I was also wondering if you thought about a case where you just relax this condition of expressivity just a little bit, where you allow maybe kind of 2 critical points per area or something like that.
No, well, that would actually be, that would sort of be very difficult to control, because the proof relies on basically very, very careful accounting of where the critical points are, right? So we use, you know, you use things like, you know, Hironaka's genus formula that would relate the genus to, you know, delta invariance, and then Milner's formula that relates, you know, delta invariance to the Milner number and number of local branches, and then you carefully look at what happens at infinity and so forth, right? And basically, like, everything has to be airtight. All these inequalities line up in the same direction, because if any of them like is not an equality, like at each point you have an inequality, but you want it to be an equality, because otherwise your you know, otherwise your vial is leaking, you know, you lose something, and then at the end you won't have the answer which Bézout's theorem predicts. Okay. And so and what you are suggesting is that maybe we should allow like one leak or two leaks. We could allow, but then we kind of lose control, because then, you know, suddenly like one of our curves could have genus 1, you know, or maybe they are still you know, rational, but maybe have two places at infinity, you know, and then just like your chickens are sort of running all every which way, and it's very hard. I mean, you can probably account for it if it's like one step away by just going through the proof and each time looking at what would make it leak just one critical point. Or, but one thing that we could do actually without too much blood spilling is we could allow more complicated singularities for the curve itself. Like I require the curve to be nodal to begin with, right? And in fact, like I could allow transversal crossings of several branches, right? Because it's easy to believe, like you, well, I need something to write on, but okay, let me move back just to free up some space. So, you know, like suppose we have something which locally looks like this. There is some other stuff on the outside, right? And here I know where the critical points are, right? Yeah. And then I'm changing the parameters of my curve, and this line, like this line, you know, starts moving, right? It starts moving, and then for some value of the parameter, it passes through this point, right? And what happens is that here I have a D4 singularity, right? And what happens is that I had three, you know, very close to this point, I had three saddles and an extremum, right? And they all collapsed together into one point, right? And then when I passed through, now I have, you know, the same two lines here, but my red line is on the other side, and my critical points emerged on the other side again, right? And it's still four of them, so I didn't lose anybody. So clearly, you know, everything was kosher when the red line was passing through that point as well, right? So I could indeed generalize the theory to curves that allow those kinds of transversal crossings.
I see.
Actually, there are some examples where this does happen. We can sometimes, yeah, anyway, let me not talk about this.
Okay, thank you.
Sure.
Next question. It might be a bit vague. Is there like a parallel series for non-isolated singularities about like this morsification or like cluster algebra description of the singularity?
No, that all the hell breaks loose once you have that. What you could have is like you can have some control when you have you know, when you start looking, for example, at links of singular curves that arise by taking, you know, intersecting a sphere with a portion of a curve that contains several singular points. You know, you get like quasi-positive links and things like that. So, once you get like a whole one-dimensional singular locus, yeah, I don't know of any theory that would work in that generality. Sorry.
Okay,
and I'm not an expert in singularity theory at all, so don't take my word for it.
Okay, yeah, thanks.
Another question about generalizations, possible generalizations.
Yes. Yes.
So this theory looks very much affine. Is it possible to replace the line at infinity by something else?
Yeah, well, yeah, it is very much affine. Well, I mean, the final count, of course, happens in P2, and we'll look at the line at infinity, you know, intensely. But right, but replacing it, yeah, you mean like looking at curves in like blow-ups of C2 or something?
No,
yeah.
I understand that probably you need some curve, but this right now it looks like a relative theory with respect to a line. Doesn't matter what line. Any
Yes.
line at infinity.
Right. Of course.
No,
yes. Well, relative, but not quite. I mean, you need to have the real, like there is a story which has to do with real algebraic curves, right? So you have to.
Sure.
But regardless, yes. Morally speaking, you're right. At some point, it just boils down to looking at how the curve intersects with the line at infinity. That's right. And instead of that, you mean we could have taken a conic, for example, or something?
Yeah, why not?
Yeah. Well, I don't know. It's a good question. Maybe we should look at it, but we didn't investigate that. It's fairly complicated as it is. So, yeah.
Is there some parameter version of this, like position of curves with respect to a pencil of lines or something like that, a pencil of other curves? There are things like that which are really maximal from the real point of view, and it may be somehow related, at least philosophically.
Huh. Yeah, no, this is, this didn't come up in our discussions. So yeah, this is a new perspective to me.
I didn't understand really why, say, two parallel lines crossed with a third one, not parallel to them, is not good for.
That's all right. That's all right. They can, that will be expressive too. So you can have two parallel, like this is an expressive curve.
But when they become pseudo-line, do you somehow disregard them? Despite they discrete?
No. It cannot come from a morsification. That's what I'm saying.
Ah, okay.
Because in a morsification, you know, this would be local branches at a singular point. And they have to intersect. Like you are losing, like things would not match. Yeah, that's the point. That in a morsification, they would have to intersect. And for this expressive business, they have to be stretchable. And this is not really, it's not that important, you know, this whole business with pseudoline arrangement. I just wanted to emphasize the fact that these two theories really are like in general position with respect to each other. I could have chosen some other examples to illustrate that.
So what is the link of singularity that you were talking about? If I remember correctly, in the work of Acampa,
yes,
there was this disk embedded somehow in a curved way, and then it was intersecting with a curve, and then you take regular neighborhood of this disk, and you read on the boundary or something.
So there are two definitions, right? So one definition is the original definition, which is like just take a small S3, intersect it with the curve, right?
Yeah.
You are not asking about that one. You are asking about the construction of the link, right? That
Yes,
Acampo
is not
right. And, right, and the construction that Acampo used was the following. So you look at your divide. So it's a variation of what I told you, but I wanted to make it simpler. So like I didn't lie to you, but that wasn't the original construction of Acampo. So you look at your curve, and so this is in a disk. Let's say the disk is x squared plus y squared less than or equal than 1. Okay? And now we take our S3 to be x squared plus y squared plus z plus u squared plus v squared equal 1. Okay?
Okay.
And now instead of taking the unit circle bundle, we're taking above each of these points, we take two tangent vectors,
Yeah.
okay, whose coordinates uv satisfy this equation, together with the coordinates xy of the point. Okay? And the beauty of this construction is that as xy approaches the boundary of the disk, xy plus y squared becomes 1. And so u squared plus v squared becomes 0. And so those two threads, they glue together, they kiss. Okay? And so over each of the red points of the curve, you have two points, right? And at the boundary, you only have 1. And they glue nicely together. And this gives the link. Okay? But instead, I just made it simpler by saying, let's just double everything. And let's make a U-turn before even approaching the boundary. And let's use, you know, a similar procedure. And then you can do it just with a unit circle bundle. It's actually a little bit of light. Like you can, if you want to keep your link transverse, then you have to do the Acampo recipe. Like you have to do it the right way. But if you just care about the isotopy type, then it's fine.
But
because near the boundary you have this this issue that whether you make a U-turn like this or you make a U-turn like that.
Okay.
And it's not like necessarily
crossing.
Yeah, but it's anyway. It can be done. So the associated links turn out to be isotopic.
Okay.
You have to really carefully look at that, but we do that.
Thank you.
I mean, I try to cover. These are 2 pages each, 2 papers, each of them 80 pages long.
Okay.
So I gave you like a bird's eye view, and I focusing primarily on the expressive business. And you are asking primarily about the morsification business. Okay.
Yeah, thank you.
Okay, I guess thank you again.
My pleasure. Thank you for